in all of these tasks, often you use a multitude of different kind of loss functions. It also kind of part of the knowledge to understand when use what. Like I'll just give a quick intro now for those of you here, and then when others come, I will give more information. So just you can start coding it. So this is the function which we need to code in the forward passes Huber loss. I believe all of you should be able to do this. Just to make sure that the delta here, this is a hyperparameter. You can set it by default to 1, or you can set it to some other value. Let me show you the other values. What will be the effect and what is the difference? Just a second. So the way how it looks like is this. So if I set it to 0, then it will be like a absolute error. If I set it to some higher value, like I don't know, in this case, what could it be? You know, like the higher value you set it, the more the shape will be like an exponential shape. Why it matters, I will explain when others come. But meanwhile, you could technically code this. You know, this is again is hyperparameter. Just make it that this is hard coded. You know, in the or you can change it from the top of the code or somewhere. You know, this is something you choose when you train the model. So in the forward pass, implement this, please. Is it clear, right? So in the template, well, if I can show you if somebody don't know where to code it. So in the template there is loss Huber. So see, yeah, so there's the blue line. So you already see one example of how to do mean square error, or y minus y squared mean value. Here you have so if somebody has difficulty decoding equations, so this means mean value. First, this means mean value. This is the hyperparameter delta, just a value stored somewhere in class. Also hyperparameter, this is the square or SQRT function. There is the division, right? The square here, minus 1, equals everything very simple, right? So try to do that, try to replace the mean square error function in the code and try to run it. And then you can also try to submit it as a finished work. There is actually one small thing missing, which we will add also. We already started a little bit, but I will explain again. This just gave so that if they sit, they can do something. Again, so okay. So the one task is in the code. In the code, let me actually show you in the code as well. There is a part. And also in the task that we should implement different kind of loss function, loss Huber. Here is on line about 146 to implement this function. So we need to implement it here, and the function itself looks like this, and I will explain why it's useful as well. So here this part means mean, torch mean. So this is torch mean. So then this delta is a hyperparameter. So how do you code hyperparameters? Let me show you. So here the loss Huber, let's call that here is delta. Delta. This will be, let's say, 0.5. Then we say delta 0.5. And if I want to actually then pass it as from the top of the code, I can define a constant, and when I create this Huber here, so I need to change, of course, loss mean square error instance to the loss Huber instance here, and then I can, if I have delta written somewhere in the top of my code, if I want to test different hyperparameters, then I can change it here. So I have self delta, which I can use here in this equation. So you do the equation yourselves now. I will go around and try to help, but not initially try yourselves. So then let's keep talking about why this matters. So I will put on another slide quickly the examples. So here there is the examples between two types of loss functions, and the Huber loss is somewhere in between. So this is L1 mean absolute error and L2 mean squared error. So the situation is following. So remember, when we calculate the loss value, then later we calculate the derivatives of the weights with loss function with regards to derivatives of the weights. And basically what it means is that in this case the jump in the learning rate, I multiply by learning rate, and the change, how the weights will change, will be much less than here. So here the weights will change a lot, here they change a little bit, right? So it is good and bad at the same time, because if my data set is very clean, my data set is clean, so I know that there is no mistakes in my data set, but in reality there's very rarely some data sets without no mistakes. Usually people who label things are really bad. So, and basically if I have a very clean data set, then this procedure is excellent, because what will happen initially, the sample is not okay. I go very fast, down, down, down. Here I go super slow and get to the best result, right? But if the data set is dirty, for example, there was a classification of objects, and then there was some lazy guy who was labeling and labeled cat as dog and vice versa, right? So then it will drop here as an error, and it will be this value basically will produce a lot smaller gradient. So the effect of the error will be a lot less, so it will be more robust. The problem with this function is that when I get to the best result, here it will jump from one side to another side all the time, jumping from that side to that side to that side to that side, never getting the best value. So it's kind of dirty data set, clean data set, right? Different ways how to do this. And then if I want to have option to tune between, if I know maybe my data set is that dirty or that clean, right? Then I use Huber loss, where I can change the shape. So if the data set is basically quite dirty, then I use a little bit lower value. If I feel the data set is cleaner, then I start using a little higher value. And yeah.
So basically the Huber is always superior because you can always adjust it accordingly.
Yeah, actually it is true. Yes, and in general, I think not many people realize that, because still, like if I teach this thing first time, of course I will just use this one, because I still need to do derivatives and explain how this works. But in general, in practice, if you do some actual production models, then this is actually superior. Yeah. So yeah, and then but again there is one downside, that we have a hyperparameter. So we already have so many hyperparameters. Batch size, learning rate, how many layers we want, what kind of hidden size we want, what kind of delta now we want, and all of these guys need to be tested. So we need to test all of the combinations to get the best result. It takes so many experiments. That's why we use also that supercomputer. The idea that we have one data set, one problem, and we send out like 1,000 different options, and then they come back and say, okay, this combination was the best one.
So the trade-off is flexibility versus time complexity, compute time.
Yeah, but also the kind of like, if the original question was about the Huber loss superiority, it adds another hyperparameter. So.
But that's the time complexity time. It takes longer to train, but normally it's just better because you can adjust it accordingly.
Yes. It's always also, by the way, in all of these options that most likely you want to get better model first. And even if you have like an embedded device where you have limited resources, then it's better to start with a much larger model, and then when you get the best result you can on larger model, then you start thinking how to reduce it on smaller, not start with the smaller. So that's the right, yeah. And then if, for example, here the good news is you find that your model works the best with the smallest possible deltas, then just flip it to L1 and train it again if you want, So it's not that bad. Okay, so please try to implement this thing, and then second I will also implement it.
Can you have a look?
Oh, sorry?
Can you have a look?
Oh, I already implemented. Okay, cool.
Yeah.
Did you try to train it?
It's running it.
Oh yeah, but is it reducing, right? So it is reducing. Okay, so interesting.
Maybe that one.
Just a second.
Maybe that one is a bit redundant because they could have just
Yeah,
written one,
but please. So it's always best not to hard code variables. So this case, this is something can be changed, right? If some other guy looks at this code, he will not understand which part needs to be changed immediately. So it's just better to have the self delta there and define it somewhere, you know.
Yeah.
That'd be safer. And by the way, you can use also not only again, this one big thing. Please try not to use NP exponents here. It's even kind of amazing that it works. But well, first of all, if you want to use exponents, then they must be from Torch library. Torch exponent as well, that works. But then you can also use the notation with two multipliers. But definitely Torch. Never ever mix together NumPy and Torch. Yeah, so see you're not using here the EX one. So see the gray variable? Gray. No, that's not gray. So it means that it's not moving. So you need to use it to pass to the model. So the self layers forward should get that. Did you do that? Self layers forward should use the EX font as input. No, as an input, that's just the one. Delete EX and push that one.
No, I don't.
No, scroll up. So now, yeah, that should work. Try again. Yeah, so go there to that line, this line. So here, this is different variable. So you're overriding variables. Basically, it should be like that. Because I'm not actually changing the list, I'm just adding the other one. Try again. Oh,
That's
man.
not
Okay, go here again. Go here, no, this one, right, scroll up. Scroll up. So here it should be 16. It cannot work with and now it's out. Yeah, so yeah, you need to replace here the loss in the system. So it's not really a method, it's the instance of the class. By the way, I think the first time when I spoke to you, I forgot to mention, as you understand in Python, you don't use new, right? You just write like loss over. Yes. So this means create instance of that object in that variable. So it's kind of counterintuitive. It seems like it's a function call, but it's actually the new creation of the object. Again, I think the very first question, it still might be confusing to some people. I will add this. So the like in kind of C type of languages, C type of languages, you create the instance, new class like that, right? If I kind of see that still some people not comfortable truly with this. So and in Python we create a new class by this way. Python. Unfortunately, the way how Python calls functions is the same way as it looks the same way. So here, if I call the result of a function something, it looks like that, and the same looks also here in the Python. So basically, this is a little bit confusing how to write this code, but it means that if this is not a function but a class, it will create a new instance of a class. Yeah.
I have a question. So I get this error message that I call the function there's one positional argument.
What's the most go back to like just no, I'm just looking like just why I see where it's going. Again, this is what I wrote in here. So if I don't use these brackets here, then it means that this is not an instance. This is just a type. You see in your code?
So in this line 166 there's
So there is a bug in line 147. So this is on the whiteboard. See? So yeah, if you don't do that, then it thinks that you are giving the type to that.
Okay, thank you very much.
Yeah, how it's working great.
Yeah.
There's the brackets too many or something like that. So the way how to debug this is just try to click on some of these brackets. Just see. Like click here on this bracket, highlights that pair, right? Highlights this pair, so this is good. This is good. This is all right. These two guys are using the column on the other end. And also never use the empty together with torch. So just always only torch. You know, because again, I noticed that in a few of your experiments, and that is quite important. Like in all of these PyTorch models do not use the MP. So basically, MP exponent or anything like that, or MP SQRT is no go for PyTorch. Instead, use the torch SQRT. So because, again, remember that we have this grad function pointer, it needs to understand what kind of function was it. If I use numpy functions, then the PyTorch, this autograd, will not understand that I'm trying to do this mathematical operation. It will just think that that's a scalar value there. So because it will pre-compute it using numpy and just give it to the torch. As you remember, numpy arrays do not have the gradient value and do not have the gradient function pointer. So it's just simple matrix, and it will have problems then. So don't use NP anywhere. NP can be used only in data preprocessing and so on. Yeah, so here, as I said, the first thing, so this guy, this is torch mean. So that is the mean value, right? Sum and divide by the number of elements. So you write that thing first, torch mean, right? So that is the first thing. Then the next thing is squared sigma, right? For squared delta. So you already have delta. So you write self delta squared, right? So this is great. So then the next thing, we need to have the brackets, right? See, as on the table, right? As on the brackets. Then in the brackets inside there is the torch SQRT, the square root, right? And then inside the square root there is 1 plus, again, brackets with squared if y prime. You already have the y prime here, see? Y prime y. Just write that equation here. Only not just everything SQRT, you know, all the mathematical functions must come from Okay. Yeah, so it means that here you have more approximately you see very close, you know? It's going to go like that.
How can we check
Square root. Yeah, it is doing something, so you just need to run for longer, see where it goes. Also, this is a valid question, which we'll answer just in a second, about how we know if this is good or bad.
Yeah, and my kind of approach, like walking like the first step and after this.
Yeah.
Yeah.
Yeah, so this means the gradient in ball, I think that's good. Because, you know, you're using some kind of probably 432 or something. If you get to some point where the gradient is too small, you know, where you can get into a good place, and the next step is super, super small, then it just drops down, and so that's possible. So yeah, maybe normally what you do is always say, first all you say here, I don't say there, you know?
So it's one variable.
It's working. Yeah, go to the
Okay, it's working from them, so I guess. No, I mean, it's like going to that's very fast. Like snow. Yes. Oh, why? No, my gradient was like 4%, so that's like. Everyone of us is like.
Technically, like, I don't even have to solve it. It will be minus.
I remember this kind, and I got like something to do with it.
Yeah, you're making me look stupid.
Like that, you know. You know, I can do it like this.
Yeah.
Before I really was
So if you don't have that step, you don't press it.
Oh, did it again.
Yeah. You're solving the problem, yeah? Put this on the other side.
Yeah, but it should like different amount of
So it's working, but I have transfer and this is another complicated because my test station is below my train.
Yeah, it's like a pro.
Why?
It's possible. It's like the difference is not huge. But it's huge. But it's almost the same. So even maybe as I say, that's very simple. And it can look like that as well. It depends on your delta. Like what is your delta now?
Yes.
0.5, right? Yeah, maybe it looks like that. You also have 0.
Yes.
So maybe this is discriminant. Maybe your model is different than the other model.
No, I have
So
you can do
the
that.
model
Yeah, like,
itself.
if I remember the formula, what's it?
That's not
B squared minus 2ac.
So the model class.
No, yes. After you've done that,
Super easy.
Is it this structure?
you have to like
Fair structure. Okay, good. In many of you, hey, listen to me. Hey, guys. So I had multiple people ask the question, which is a good question. So how we know if the result is good or bad? So they maybe like, is it actually like getting to real like price or not? If you see the losses is converged, but maybe it's converged of giving us like really bad predictions of car prices, you know? Like it might just be off of 10,000 euros or something like that, and it converges, and you think, okay, we trained the model, but we don't know if it's good. So to get the answer for that question, there is another small task which is also added in the 4.2 section. Let me quickly get that. So that is the option to calculate the normalized root mean square error. I will move this to the Jamboard and then ask some questions so you can look at this already. So what is the difference of this versus the just the Huber loss or mean square error? So what difference between this and these guys? You know, L1 and L2. So why this would help us to understand if our result is good or bad. By the way, this is not the only way how to calculate it. Okay, so the answer to this is that first of all, this is root mean square error. This is first difference, right? That there is the root square, so we get back to the real value, kind of. Then we divide it by the standard deviation, or the difference of all of the values that we get from that data set. And basically what we get is range from so basically about kind of range from 0 to 1, and 0 means perfect and 1 means very bad. So we could inverse it other ways, right? Like 1 minus, and then we could kind of think that 1 means like perfect. Like if we add here 1 minus, then that means that basically this is perfect and 0 means very bad. And if you get something in the middle, then we say there is a room for improvement, right? So the prices are kind of good but not great. So if you get this value like in the so with the usual mean square error, I don't know the range, right? It can go from infinity to 0. We know the 0 is perfect and infinity is bad, and that's not good. We don't know the range, right? Now we know the range. We know that like about 1 is bad and about 0 is great. So and if we are in the middle, then we say that our model is halfway, right? So that's one way. The other way is we can also not use this part as a standard deviation. We can just calculate the absolute distance between these guys, right? The kind of, let's say, average or maybe maximal distance between those guys, and divide it here. It would also give us normalized root mean square error. That is not the only way how to write this equation, but this equation helps us to understand if our model is good or bad. Because otherwise it's unbounded. We just know if you get 0, then it's great. But what other things we don't know, because it's the infinity, right? So, and this is called metric. So you will see also later that we have the loss function, and then there is a lot of metric functions, which are functions to validate the result. Is the result good or bad, and how good it is? But they are not directly used for training. We could use this function for training as well. But if we implement this for training, then it's not a good idea to also use it as a metric. It should be two different ways to kind of check if the result is good, or more ways to check this result is good. Another alternative to this thing is called R2 score, for example, or you can use all sorts of other functions to kind of estimate if this result is the best we can get, you know. So I will show you how to implement this, and then we move on. Yeah. Yeah.
Doesn't work anymore, and I don't know why.
Doesn't work anymore.
Yeah, now I've tried some things to fix it, but I think it's the second time it didn't work anymore. All of a sudden.
Yours is working?
No.
Yeah. Unexpected.
Yeah.
Torch exponent doesn't work that way.
I mean, mine is doing something. I don't know. What was this error?
Well, you have white print, that's right.
Is it y prime or?
Yeah, like if you would make your own derivative, then it's very important. If you don't make your own derivative, it's not important.
But if I would,
then it's important, because you need to know which one comes first.
What would be the order?
The result would be exactly the same. If you change it, just the derivative changes, you know? Yep. The equation for derivative changes, but the gradient will be the same both ways.
But it's the normal way to go?
No normal way, you can do it anyway. So it's like it's the same value, you know?
Yeah, okay.
It's just that the derivative is different for one mode. Okay, good. So that's okay. Let's jump in back in the code. Make the normalized root mean square error. So again,
It's still not working.
sorry.
It's still not working.
Okay, we'll come look at that. Just a second. We'll try to write this one, and then. So n RMSC, root mean square errors, RMSS, I don't know, like, or just let's call it metric, validation metric, validation metric, like that. So that is that. Then here, it's the safest place to do this is after the after the calculation of the gradient, because if I do this before, there is a chance of me messing up the gradients. I could interrupt with the function graph, do some equation which can also affect the result. In most cases it will not, but like as soon as we start more complex models, it might be easy to mess up things. So it's better to do this here in the RMSE. So and then there is also options how we want to do this. Either we want to calculate this over whole data set or just the batch. Just the batch would be easier, I guess. It will not be as accurate, but it will be easier. So what I mean, the whole batch is the mean value of the y. So just a second. So this value is actually. So we could actually do the either way. I don't like that the square bracket is inside there. I mean, square is around it. I will put it inside it. Mean. So then torch sqrt. So this will be this of y minus y prime, and this squared. So this will give us natural value, the real output, but now of course it will not be the real output because it's still not inversed from the original mean and standard deviation, but it's good enough for getting the result. So sqrt. So then we have this guy set up. This is set up. Then what we can do is maybe divide it by only there is another small issue here. Torch mean, we have two-dimensional output. So what I want is to remove the batch dimension here, the comma dim. So if I don't have this argument,
Can you scroll a little bit up?
oh sorry, yeah, for sure. So if I don't have this argument at the end, I just have torch mean, I will get one scalar value, which is okay, but at the same time not okay for this task because we have two outputs for each batch sample. We have the price and the number of owners for car. So that's why I want to calculate the mean value over the batch samples and still get. So this will produce the output, the first part. So this first part produced the output. So initially we have batch, comma 2. So these are predictions for each of the batch samples, and after this we get 2 like that because it will be the mean values only for those samples. So that's good. Then we need to divide it. So we could actually use existing function here, torch std, standard deviation. Standard deviation of, I guess, but actually we could maybe access even the whole dataset stuff. So y minus dataset full y, yes, y, except this should be mean. We'll see if it works, hopefully it will. Okay, I will split it in 2 parts. I always encourage everybody to split everything in multiple parts to make it easier to debug. So std y, so this will be the first part. And this will be the torch mean of the whole dataset y's with dimension of 0, so I don't want to include those things, except the type here is missing, so I guess this will be then np. Yeah, so as I said before, we should not use the torch and numpy together but in this case the y is actually numpy, but we'll see. Maybe I will leave as a torch, and if it doesn't work I will change it to numpy. Okay, so I think we're done with the kind of basic way to doing this. Except maybe, yeah, this seems to be about right. Just a second. I don't like it. Okay, let's change the equation. So I will use this one as that, and then axis put dim 0. So this will be correct equation. And here I hope that this will work. We'll add a breakpoint, run it. Oh, sorry, I will get back. Okay, yeah, it doesn't like that this is not. So, okay, so let's use npstd for this one, just because the full array is in the numpy format. So, okay, there is a problem. Okay, so this is axis. Okay, let's try again. Oh man, what is this? Just a second. Okay. It didn't like my experiment. We will get okay, let's rewrite it again. So the way how it was before. So torch from numpy. I hope this is gonna work. This is definitely not memory efficient. The standard deviation of y should be calculated before doing this stuff. So like before the for loop, but just for the point of being, we can use it. Okay, so we get the result here. We even also get the gradient function, which might not be cool, but it is there. So yeah, so we get these ones, and here we also need to move this to data numpy. So this is the way, which I guess I forgot to mention. So this line of code from numpy helps you to get the tensor to numpy the numpy to tensor format, and data numpy gets you the other way around. So this is very useful at the end when the model is trained. When you don't care anymore about torch, you want to use just the actual values, then you need to know how to convert it back to the numpy. So I copy these 3 lines of code. So just 3 lines of code, and this is working. So that is good. Then the last thing is, would be nice to plot it somehow, right? In the plot. So to plot it, I will add here some extra stuff. So this is a loss plot, right? So if I add here a few other guys like these, nRMSC, loss plot. So nRMSC plot test and train. So these things. I'm also adding that to Jamboard. And then if I had them, and then I add here the actual values there. So loss plot train from the val metric. Again, we could calculate these things for each of the metrics, for the price and for the number of owners separately, or we can use calculate them together as well. So test. So I added here those 2 guys. Adding to the slide number 12 the equations. So the slide number 11, there are a few lines which I changed. Slide number 12, few lines, and then here below there is just adding those things to the plot. Again, the matplotlib, very kind of powerful library. You can add all sorts of things here. So here what it means is I want to add a new line here. It will be called the nRMSC train, and this will be so red. Then what is the C? Like, I guess cyan color. Then I can add some green color, I can add blue color as well, and the line means a line. If I add dot, then it will create a dotted line. So it's kind of easy format to add things to the plot. So this is this again. So for the displaying data, you could look at matplotlib. There is lots of functions and ways how to display data as a bar charts, pie charts, the multiple lines, so on. So we'll see. Hopefully there's no bug. Yeah. So here the result. So NRMSC test is the blue one, and the green one. So it's interesting. So we see that the test value is red. Okay, now they are reducing at the same rate, but initially the test value was much worse than the other one, and now that they should stop. Like if it gets to the 0, then it's perfect. But in the bottom part, I see only the losses. I should also display the other values as well. So let me see. Okay, now it also diverges a little bit, so that's interesting. Let me add here. So, by the way, in just a second we will start working on classification as well. So if you're not getting with this along, you can also just jump in the next part. So just a second, I will go around and help you as well. So NRMSC train. I just adding these for myself to see what is the value in the console. -1 NRMSC test. NRMSC test. So now, if it gets to the 0, then it's perfect. If it's closer to 1, then it's not good. Okay, so yeah, we can see initially the value was 60, so 60%, kind of like about halfway, and now it's getting better. But it's even though the loss plot looks kind of, so we'll see. I don't think it will get to very good value. I don't think it will get. Maybe it will get over 50% kind of, but we'll see. So okay, so
yeah. So first my Huber is still working.
It goes to Huber also.
What was it? And also the
trick.
Okay, yeah, that's let's go there first to that line. So scroll a little bit up.
Oh no.
Okay, here to the losses. Below the losses create the volumetric. No. Below the losses go up. Below the losses, yeah. So the line below this line. Yeah, or there, yeah. Create the same. So
this one. Okay.
After this one, create a volumetric as a list. Yes, now that will be good. So just a second. Okay, we'll see what happens then. Okay, there is something also. Can you go back? Stop it, please. There's something interesting regarding that. For example, why this is highlighted. Can be undefined. Okay, you actually need to move this out inside. Go back. Tab here, inside there. No, that's in the wrong place. That's one. Let me see that. No, it will not help the training. Just a second. So it's still NIM. Go to the loss function, please.
What was it again?
Yeah, this one. Yeah. That might be the Uber loss function. So I go to under 40%. So I get 0.4. So it's below halfway. So it's kind of a 40% error or something like that. You could think. So.
I don't know.
Oh, there is a mistake in your equation. I think so. So
Let's go.
yeah, the SQRT part is not here, it's here. So like that. Something is
Doesn't look correct.
Yes?
Doesn't look correct, right?
Well, let's see, it looks okay. So the plot looks okay.
The loss is at 0.32.
Yeah, but that again, that doesn't. So depending on the structure, it might be all sorts of things. It's if you implement the NRMSC metric, you see that that would be more realistic. So, but I don't know. Maybe it is like that. That's they kind of tell that it's working. So can I help anyone? No, so yeah, go to the place where, so control button on this guy, no, the other one, loss, no, below, no, yeah, okay, yeah, but then you need to define,
Is the code forgot?
define these two guys at the place where you define the loss. No, no, not that, not that.
Das ist mit dem NR.
Go add them there, yeah.
Okay.
Now it makes sense, right? We can go all to anymore. So here, these guys, so the val metric, can you scroll up please? So here the val metric equals the list, should be added below the losses. This. No, not leave it as it is. The val metric itself, the array does not exist there, you know?
Oh, yeah, okay. I should have added
No, not inside that one, but here below, yeah. Equals list, empty list. Yeah. And then these guys should be one tab below because right now they are only in the train part, you know. So there's the if this is a train, then only that executes, right? And then the last thing would be these red ones are missing. So the way how, so you copy, for example, that variable name. And then scroll up, please. Up, see, there is these guys. So below those also make those. Yeah. And the other one. So, but also there's a list, right?
Yeah.
Yeah. So then it should work. Hopefully.
Can you please show in your code the axis again?
Sorry. Yeah. We'll kill it. Yes. So axis. Yeah. So this part. Okay. I will also add this to Jamboard.
Yeah, but I deleted something.
Yeah. Oops. Okay, so as soon as we're ready with this, then we are completely done with regression task and we'll move on to the next one. So
In your line 107, is it on purpose that they're sending just block train instead of NRMS?
oh, you mean just again? No, might be some mistake. Let me look. What line? Which?
107, I guess.
What line? 100? What?
And 7.
197. Yes. No train. Yeah, it is. I think the correct. So here the. So the NRMSC train. NRMSC train.
No, 107 in the
here.
So this should
Yeah,
be-
so this is wrong. This is wrong, correct? So we need to change. That's a typo, yeah. And anonymous. I will update. Just a second. Good catch. Yeah, that is a good catch. Good catch for this. Okay, so then let's. I will open also the next task here. So the implementation of the classification task. And there is a new template. Get the new template, and we will go quickly over this. There will probably not cover every single detail, but you will get the understanding and be able to implement these things. So the classification task, and it will contain things which you already understand. So let me show you the idea. So we will have the copy image content. So this will be classification. Okay. Classification.
Felix, was hast du für ein Loss ungefähr?
Just a second. Okay. Yeah. Okay. I will come and explain a few things.
Hab das auch als Mail geschickt.
Geil.
Aber es ist
Ja, ich
weil die Google ist noch dann auf einmal auf das Ding angucken. Das hat er gehört, ja. Passt das? Ja, wenn ich
Yeah, I think.
ja, Aussage man hat, das ist extrem ausgeschickt. Also ich glaube, das ist schon das letzte Mal. Das kann man auch. Das ist ein
Axis and change this to NP first one. Very interesting installation. So not you have the.
Was hast du da bestellt? Machen wir das kurz. Gestern. Ja.
Ah.
Das kann es aber jetzt nicht so. Ich glaube, das kann man üben.
Yeah, it seems like something with the installation, so very strange error. So maybe just comment all the. So okay, so let's talk about classification. So let me actually show you the template, and that will hopefully also help us understand the stuff. So this is the new template, last template for today. So the same data set, but different configuration. So the difference in configuration is following. So we move to the X side, the three categorical classes, the brand, transmission type, and seller type as an input. And we move all of the scalar values also as an input. Year made, kilometers driven, owner, number of owners, and selling price. All of this is the inputs, okay? And the output of the model, the Y part, is just the fuel type. So diesel, petrol, LPG, and so on. So basically, that is the output. So it's actually written as an X, but this is Y, and these guys are X's all. So that is the configuration. And the plan will be to predict which class belongs this car. I give all of this information about the car, and I want to understand if this car is more likely to be a diesel or petrol car. Is it clear? So, and we can classify all sorts of things, right? You can imagine like Well, like, is this that letter? Is this an attacker or not attacker? You know, like if this is malicious network traffic or not malicious, and so on. So then here we need to encode this Y the same way as the embeddings, but in this case, this would not be very advantageous to have these guys moving around the space. We could make that kind of model, but it will make a lot more code. So for this particular example, we will see just in a second as well. The loss function requires that the output will always be in the format of one hot encoded vector, or this what we just already see, 1 0 0 0 0 1 1, so on. So let's check that you understand. So what will be the encoding for the diesel here? So if this is one hot encoded vector, or one hot encoded vector, so what will be the encoding here? So how many classes do we have? 4 classes. Well, so what should this look like? 0 0 0. Correct. So this is 1. So how this should look like?
0 1 0.
Yeah. So you're getting it. The other thing is, which is good about this representation, is that we in information theory we can also assume that this is not only just like a vectorial representation, but we also can assume that these are probabilities. So 100% that this is a diesel car. It cannot be 50% diesel, 50% petrol. I once had an experience like that, not good one. So if you try to pour the wrong fuel, right? So this is not 50-50. This is 100% each of them, right? So maybe for LPG you can use it, but in this case we assume that we cannot mix them. This is kind of very important assumption. Like I cannot even overstate it, that for all of these classification models, if you want to start calculating that some of these classes can be 50-50, you cannot use the loss functions which you're going to use today. There is a completely different way how to formulate the problem. So it's again important to understand what are you using, what kind of data, and so on. So the methods. So here, the way how we then encode this thing is as one hot encoded vector. Maybe we can find some easier way, but maybe I just want to do this. Okay, so yeah, let's do then with the NumPy type of thing. So self y mp0. So there is a function that creates a array of the zeros. So here this will be the so this will be then the length of y. So this is the number of samples, comma, number of classes. The number of classes, we have only 4 classes. So, and then this will be, oops, sorry, the type mp float. Might, yeah, hopefully it will work for most people. So then this is this. Then we need to set those values according this method which we wrote above. So to do this, we can use nice properties of the NumPy arrays. So one property looks like this. So what we can do is range. So the first means select each row separately one by one, range. So len y, each row separately. For each row, select the correct column and set it to 1. So basically that's it. So this makes us the one hot encoded vector here. Okay, I will wait you to catch up with this one, then we will move to model implementation. I will try to find where is it here. So we'll here. Yeah. Okay, cool. So yeah, we'll go around. Yes. Scroll up. Here below this guy, losses must be the same kind of wall metric. You understand? It's not defined. It's not defined. You need to define the list below this, below this, below this. No, below this. Of course, because that is the for loops. Here is the wall metric and as list, you know. And then the same thing like for these guys, but at the location where it's defined the loss, you know. Just a second. I will go around it. Okay, and this is interesting error.
I mean, it should crash, yeah. So very nice. Yeah.
Okay,
There's
here.
a bunch of different errors towards
This is a
good data. Now it is in the numpy format. So here we change from numpy to torch and share from torch to numpy, you know. Now to try to run it. Yeah, I will go around this.
Do you know why I'm getting the error? The SQL report?
It might mean that the version is different, but I think to use this, can you comment out, try out, comment? And then maybe it will work it out. Let's really see. Okay, the Y is not the Y. I will come to that side as well, but I see interesting error. I want to check if I also have that error. So if I add here, by the way, in Python there is funny keyword called pass. So that means do nothing. And, so if you have a virtual function without any implementation, you could add pass. I use pass that I can add a breakpoint, you know. So if I try to run it, no, this is wrong. Try to run it. By the way, when you run it, make sure you click left click to debug. So it seems to be working. So I have Y's. Did you use the new template?
Yeah, of course.
Okay, but in the new template, the Y's should produce this thing, so it should be there. I will go. Okay, let's see what's up here. Okay. But you're all running the previous code, right? What might be, it seems about right, you know, like it's at the end, like I don't know, it's always will be a little bit different every time you run it, you know, because this is all a lot of random stuff and random initialization, and it can be a little different.
Yeah.
All right, no, you're right. This seems to be strange. Yeah, they are overlapping. That's because you're just duplicating the second axis. You can also create like up plot, down plot, so I can show you that as well later. But yeah, you're right. This seems strange that it is kind of going in the opposite direction. Can you show the NMC agreement? Just a second, just stop please. You want to scroll down, stop please. Okay. Stevie. Don't see anything bad about that. So I'll scroll up maybe. Yeah, let's scroll up to the model. More please go to the model. But now for you it goes down. This like I can't. This is one of the experiences that you get now is that when there's something wrong with the actual equations or like the data configuration, very hard to dispel. Right? Like if the error in code, then I can give you immediately. But now if you look at the model, it seems about right. The model seems about right. the loss seems about right, the equation for MSC seems about right, so somewhere is a problem, but I cannot identify it immediately, so like we need to move on, and then later I can, if you submit, I can move it up. Yeah. Better?
Yeah. I can't tell you why. It's
Why? The plan?
yeah, I don't know.
Just that breakpoint after the verb, yeah.
There's a lot
On this one. Yeah. Run it like the bar now.
Das ist ja eigentlich dann gegen den, was du willst, oder?
I think no, the problem is scroll up.
Something like
Scroll down. So see the scroll down. So see there is a tab here, and now you messed up tab there.
Because of that.
That tab.
Yeah, because of the
Yes,
tab.
because of the
You know it's a common.
but then scroll down.
And you know?
So see.
So this
So no.
block is the problem.
So these two lines are now in the wrong scope.
Why do they need to be?
They need to be with a tab inside the function. No console. So just those two lines. So these two lines are inside the constructor.
Ah,
Do you get it?
Yes, yes.
Okay. Can I help you?
I mean, we get the same kind of error.
Yeah, same.
Is this a new template? You need to use the new template. I'm not sure. It doesn't look like the
Yeah,
new
I
template.
mean, it's like new type. We all got the same code.
Yeah, it's not implemented. Okay, so we will implement it now. Now the other things, it will not take too long, and we'll explain a few other things. Okay, so before explaining the actual classification, loss function, and the process how this works, let's fill in missing gaps here. There are a few missing gaps actually. So again, there is actually missing we can copy some things from previous code, by the way. So drop last for the train. So this would be nice to have the same thing here, but not. It might work also without that. So, unfortunately, I have a subset which is not defined anywhere. So, okay, let's skip it. Hope that there is no small batches. So then the model and loss cross entropy, right? So the model, let's write the model. So the model we can use that's kind of the same as before. It will be very few differences. So where's the model? So I encourage you just to copy maybe the whole stuff. So the class model from the previous code to this one, there will be key differences, but the base structure will be the same. So if I copy it here, I will highlight also the differences. The only differences are that the input size changes, because remember we moved the scalar values up there. So the input is now 4 scalar values plus 3 embedding size values, because we moved the fuel type out of this equation, right? So we add there instead of 4, 3. Also, instead of 4 here, also 3. Instead of 4, also here 3. So maybe I will highlight these things in the Jamboard so that everybody notices them. Okay, but before I do that, at the end here we need to change that we want to predict 4 probabilities, not 2 anymore. But now we have the diesel, the petrol, the natural gas, and the propane gas. So what kind of so we need a probability of what will be the car, right? So you get the idea, right? So we have the output of 4 probabilities for each sample. For each car, we have 4 probabilities of different types of the fuel. So these are the only changes in the model. I will post this on Jamboard, and then we will start talking about this more. So in just a second, make sure that you get so far. So I'm putting this on Jamboard and highlighting these main things. So just a second. So what I changed here, I changed that we have 4 scalar values and 3 class embeddings. Here we have 4 probabilities. So this is 4 probabilities of different types of the fuel. So for each sample, for each batch sample, for each dataset sample, we will always predict 4 types of probabilities. So this is good. Then also here we changed to 3. Here we also changed to 3. I think the code will still not work yet because there is loss function missing and a few other things. So first things first. So my question is here. So if we are predicting 4 probabilities with this kind of model, like, can we do better? Like right now, what will be the output range of this model? So what kind of probabilities we can predict with this model? What will be the output of the vector? What do you think? Like scalar values, approximately, you know, 2, 3, -3, 4, like what will be the range? What do you think? So let's start question from other way around. So normally probabilities from 0 to 100%, right? 0 to 1, right? Like 0 is 0 probability, 1 is 100, for example. So what will be the output here? No, so here the output will be unbounded because it can be anything. It can be minus infinity to plus infinity. So the probabilities, so because there is the last layer is linear layer, which you remember that if you have this axis, right, and I plot anything, I can like get anything out, right? It can be like minus infinity to plus infinity. So it's in unbounded. So then what we could add at the end to have a better model, what do you think? So the sigmoid, for example, remember sigmoid, did you look at the sigmoid function, right? Yeah. It is from, what is the max value for sigmoid? 1. You know, minimal value? It's actually 0, but there is tan h, which is -1, but 0, 1 to 0. That would be better, right? If we add here at the end sigmoid, that would be first improvement. Then all of the values that comes out are not just from minus infinity to plus infinity. It looks more like probabilities, right? That would be good. But we can do even better, because if we add sigmoid there, then the sum of all of the probabilities will not be 1, right? It will be anything in between. It can be up from 0 to 4, right? So we could then kind of normalize in things, but it's still not really a probabilities, right? So the way how to solve this is to use the softmax function. We will look at that. So that basically this is the last linear layer, and the output of the last linear layer usually called logit. So this is a term in machine learning, because you can use also this output in some other manner. And then you apply softmax, and then you get actual probabilities of the results. So let's look at one of the examples. Again, so here there is an example of the, let me move it here. So the output layer gives us some kind of unbounded values. We apply a softmax function, and we get bounded values. And the sum of all of these values is 1, so that's also good. But then the reason why we use softmax, there are actually multiple reasons, but the simplest reason is, I guess, this one. Let me show you. So the simplest reason why to use softmax is that the actual result which we want to target is the one hot encoded vector, right? But the actual result is like to calculate the I have some kind of like, I don't know, like argmax function, you know. So basically, let me see. So if I have this guy here, and I want to convert this one to the format of one hot encoded, this is not really possible. I will select argmax, get this one as 1 and everything else as 0, but that is, I cannot get derivative of that function. There is no derivative of argmax. So we need to find some function which is as similar to one hot encoded as possible. So I'm adding this example because the norm_max function. So where is the norm_max? Let me quickly find it. This is something probably everybody have used in some capacity. So I don't know, like in when you're calculating some kind of it will give you 100%, so any values, and then divided by sum of values, right? It will give you also 100% total, but they will be a lot less similar to the one-hot encoded vectors, right? There will be a lot less the difference. So it basically, if the value here is like this 2, 4, 2, 1, I pass it to the norm_max, I get this value. If I pass it to the softmax with exponents, I get much bigger difference between the highest class and lowest class, and it's much more similar to this one. Do you follow, right? So anyway, so again, the reason that there is this function softmax with the exponents here and here, which makes the result of the model more similar to the one-hot encoded output. And we are kind of helping model to produce the result what you want. You don't want to give the model, first of all, we don't want to just give the minus infinity plus infinity, very bad. We don't want to give the model just a sigmoid that the total is 4, again, problems. We want to give the model something that is as similar as possible to what we want without touching the data itself. So it's all about these deep learning models, which you'll see also in following sessions, is to shaping the architecture of the functions without touching the data itself, so that it creates the easier job for the model. Okay, so that's why we use the softmax there, and the softmax function looks again like this. So it's exponent of each of the elements. So this divided by exponent of sum of elements. Again, you can invent some other functions to have even higher difference, but this is good enough. So we use that. Let me show you how it actually then works. So if I transfer here, so here what we need to do only is to add a new layer, torch nn softmax, and dimension -1. So we want to calculate this equation over the 4 probabilities, not the batch size. So basically, if I add here even 1, it's the same. So the first one is batch, 4, and I want to calculate it over the 4, not the batch. So that's why it's there. So I'm adding that as well to the Jamboard. And then the last missing piece will be the actual loss function. And the loss function, again, what I want to highlight is that the loss function which we will use works specifically with the one-hot encoded type of probabilities. If you want to have like probabilities where something is 30% of that, like 60% of that, 10% of that, then you cannot use the cross entropy. So then you need to use the KL divergence or some other functions, because they are not designed to handle this kind of result. If somebody is interested, I can explain that in detail as well later. So basically here, the loss function looks like this. It's also added in your task, by the way. So this is the this cross entropy function, and I can also show how it visually in the plot looks like. Just a second. I had the plot somewhere. Okay, the logarithm plot. That will be good enough because it will help to understand this. Again, few things about this thing. So this will be called categorical cross entropy function. So this is what we use for the loss function when we do the classification. So the function itself, all of this part of y vector, or multiplied by logarithm of the y prime vector, this part comes actually from information theory, where there is the entropy, cross entropy, all sorts of those equations. It basically originally was designed to calculate what is the loss of data of the bytes sent over transmission. Theoretically, what is the limit of how many bytes you can send over some kind of limited transmission requirements. But basically here, this part of the function comes from that kind of line of research. But nowadays, there are alternatives, like, again, all of these, this theory is developing. So this is classical, all over the world, everybody used this for classification, but like recently, like in the last 3-4 years, like Google, for example, produced the focal loss and some other loss functions which are not derived from the theory, but just found experimentally that works much better. So it's kind of, it's not really that in deep learning everything comes from theory. Sometimes you find something that works better even though it's not coming from derived theory. So in here, to understand how it works is that the y prime, so again, what will be the range of the probabilities for y prime here? Values from 0 to 1, right? So from 0 to 1, here the logarithmic function, 0 to 1 is here, right? When we get 100%, we get 0 here, right? So 100% probability gives us 0 here. I see that you are all like a little bit driving away, but hopefully you can follow a little. So we cover this one and then we will end. So basically, if we get 100% or 1, basically 1 means 100%, then we get logarithm of 0. If we have like close to 0, we get like minus infinity. That's why we have the epsilon here. So this creates this part, and then on this part we have the actual real probability. We multiply this together and we get the loss, how good is the result. So as far as this is from the actual value, the bigger the difference, and here is the minus sign. It will flip everything around. I will give you an example here on, yeah.
What do you mean by real probability? Like we have to know the probability before we use this?
Sure,
question?
definitely.
Okay.
Because the data set is labeled. In the data set, some person like entered the cars, right? And like the data set is the database of the used cars, right?
Right.
And then the person added that this car drives with that kind of fuel, the diesel or petrol. And then we say that this is 100% petrol car or 100% diesel car.
Right.
Okay, so let me show you what I mean by this more. So here, the y's, these guys, the y's will be always defined in the same way. So, for example, in this case, there will be the so this will be the, I guess, what was the diesel first or petrol first? So diesel first. So this will be the diesel car. So 0, 0, 0, 0, and the model will predict some kind of value here. So the model will predict, for example, that this is not diesel, this is petrol, okay? So now what will happen is that, so just a second. Yeah, so what will happen that this will generate a very large loss because the 0 here gets us value somewhere here, below, like minus infinity, like let's say minus 10 or something. So minus 10 multiplied by 1 here, all of the zeros are ignored here, right? See, if we multiply 1 by 1 like that, if they are two vectors, this is not dot product. See, there is no dot signs here. So these are just a simple multiplication. In mathematics, if you have a simple multiplication, you don't add here a dot product sign, you know? So sometimes you add this Hammond product thing, but here is nothing there. So this is the simple multiplication. So the simple multiplication gives us that I'm interested only on this variable. So this will produce some output here. All other guys here will produce zeros, right? Is it clear so far? Right? So, and this guy 0 will be converted through the logarithm. So here is the logarithm, right? So this will give us the very low negative value. So then 1 minus that low negative value, and then at the end, here is also minus sign. So we get it back to the high positive value. And then in case if here instead of 0 we will have perfect result, right? This will give what kind of value? So what will be the loss value now in this case?
0.
Yeah, 0, because here on this end, if we get like 1, there is 0, and it doesn't matter if there is 1, there is 0, it will just get 0. So it or a little bit over because there is epsilon. But basically, yeah, so that's the idea, why to use it and how we use it. Again, it will not work if there is the probabilities in between. It will then not converge. It will kind of work, but not really work. And then at the end, the last thing which is missing here is the this guy. So this is weights. So this is not learnable weights, but these are class weights. And we are using them because the number of cars in dataset for each class is different. So the petrol cars are much more than the gas cars, right? The natural gas cars. So, and if I train the model just using without this guy, so if I normally they don't add this. So if I remove this, then the model will learn perfectly to recognize petrol cars and completely ignore the natural gas cars, because basically there are so little, and the model says, okay, there are so little samples, so little effect to the loss, I don't care about them. I will always just predict that they are petrol cars, you know? So that's why this is kind of a regularization term that helps to make sure that we have the, we also take care of those rarely found cars. Okay, so let's jump in the code and make this work, and that will be for today, because it takes, I think, a lot of information. So here, okay, so the loss function, we need to find the loss function. Loss function. So here, the loss categorical cross entropy. Actually, not too hard to implement this stuff. So let me think how we could do this. Okay, let's start by implementing without weights, the most basic stuff. So minus sign in front, it doesn't matter if it's in front or in the middle part, it's just that there is. So the torch mean of y multiplied by torch logarithm of y prime, and here it's actually important the order. If like you had a question before that is the order important, here the order is important, because if I just change it over, then it will not work anymore. So it will work only if the order here is correct. So then plus e minus 8 the epsilon, so small division, because logarithm from 0 doesn't exist. Again, so super simple function. I don't know like what can be even more simple than this, you know, like just a few characters. So now I'm adding this back to the Jamboard, slide number 18. Okay, while I'm adding to the Jamboard, okay, so I can actually try to run it and don't distract you, hopefully. Yeah, ouch, something doesn't work. Okay, confusion matrix is not implemented. Oh, sorry. And also the actual model running is not implemented. Okay, so forget about weights so far, just implement it without weights, and then we will add it a little bit later. Okay, by the way, so I'm added this to the Jamboard as well. And I just want to move on to the actual the for loop, which is missing here. So see, there is missing this part. By the way, this part we can also copy from the previous code. So just let's copy the whole stuff here, these 6 lines from the previous code. So the actually the y prime is calculated from model forward x classes. Loss function output, all of this stuff completely the same. So that's great. If I run it, by the way, classification tasks are much more nicer to estimate the results. You know, you have the accuracy and so on. Okay, so it's falling in this line. If you can comment out that line right now. Okay, no, it can't. Oh, sorry. I will get back to that. So just a second. Percentage, blah, blah, blah. So let's write it. So just for the time being, you just put it as 0 here. Percentage is 0 here if it fails. So now this is the main part to run the code. Running, hopefully there will not be error anymore. Yeah, the loss is reducing. See the plots. There is a more interesting plot. So in this plot, we also have a confusion matrix, the accuracy matrix, accuracy results, and so on. So, but it's working now. With the so what I did, I added these 6 lines here, 7 lines here, and I also added this one line here just to change because I don't have yet confusion matrix, and I want this to run without that. So if I scroll back here, the model running part is this one. Let's make sure that everybody gets it working so far, and then we will add a few extra things to make it actually really interesting. And in Jamboard, both parts of codes are added, which I changed. So maybe also I changed this line.
So, but what should you like copy from the last code?
Yeah, again, so see, I have a color. So this part you need to copy. Only this part, like few lines, not everything. We'll try to see if you get it running so far. And then we will add the accuracy as well. How many on the errors, or you try and just catch up? Okay, you is working. If somebody needs help, let me know. Wait a little bit for you to catch up. Yeah.
So my ID is called Cascade is not installed.
Try to just, if you SQL an error, try just to remove that line. It was left.
No, it doesn't work. I had to actually install it.
Yeah, just to remove that line. Yeah.
But I counted it out, it didn't work later on.
Okay.
Cascade ohne Import.
Ja, du musst aber installieren. Ich habe das eben auch auskommentiert, das ging später nicht mehr.
Aber da kommt auch dann 82 und 82 kommt auch irgendwie so ein SQL.
Ja, du musst es installieren. Wenn du es auskommentierst, geht das nicht. Ja, ich habe das auch gehabt, das geht nicht.
Yeah, so let me know if somebody I can help. But just let's make this this model learn, and then add the accuracy calculation. Then we will land very soon. So it's not that there's much to do yet. So what I did is I added the percentages 50 or 0 or whatever, just because it's not yet available, you know? If I can help anyone, let me know. Okay, cool. So those of you who finished that part, I can challenge you to try to calculate accuracy. So I will show how to do this, but basically the y prim contains batch, 4, and the 4 means the 4 dimensions of probabilities, like 100% of that car, 100% of that car, and so on. And then the y means the real probability. So we need to calculate where they match. That means that is the correct classification. So you could try to calculate the accuracy if you want. Okay, so it doesn't work. Yeah, go to that line. So that I comment out that line. And the add instead percentage is 0. Because we don't yet have that.
This one?
Yes, I added because it will be added later. Okay. If I can help anyone, let me know.
I got some kind of syntax error.
Yeah, there is missing comma there. No, not there. See the red line? There is this is not the small letter but big letter, and the torch NN. Oh, yeah. Yes. Because what you call is actually just a function, not the object class. So what here in this part, these are not functions, these are the class. All of this is the same torch.env module. All of these guys are torch.env modules. We are creating instances of them. But what you wrote with the small letter, that's yes, but that is just the actual function, not the class of that function. Can I help anyone?
So if I'm out to comment this SKL module,
Yes.
then we have some kind of dependencies because this method is using.
Yeah, for
So I try.
okay, so try to Zinka, let's go here to the Python packages and try to sklearn there. Or yeah, yes.
So I tried to install it already, but it gives me.
No, not there, not there. So can you go here, press and stuff? Did you do that?
Yeah. Now I go over the settings. Yeah.
Fail.
Fail.
Details. Some kind of we'll try in pencil. What is the correct package? So what we could do, index is trying, so I used here the statify function so that it has the same number of classes like the cars, so like the distribution in train and test set. You could try to not use that as well. Can you go back to the previous template? So let's quickly fix it without that library. It's very bad that I don't have it here, but so here you probably can try to use similar stuff as this one. Let's try to just replace this one, okay? There is the so this all this section. Let's try to replace it by that. Try to run. Remove that.
Yeah.
Yeah, that's different error.
Yeah, I have to change
Yeah,
the
sure.
other parts.
Okay, cool. I can help out to somebody else. Okay, so let's then calculate that. So this model is much more nicer than previous because previously we had like guessing the car price and then we try to do this normalized root mean square error, but still it doesn't feel right. So what it actually means, 10% accuracy on car price, you know, or something like that. It's kind of not really confident way how to. But with accuracy, it's very easy because you know, like we can calculate if this is correct or not correct, if it's over 50% or under 50 or over 80 or so on. So here what I suggest to do is to calculate accuracy in this way. So here there is the line of calculating the accuracy. And to do this, let's select the samples, like the values with the highest probability. So the y index, highest probabilities of y index will be the y argmax dimension of 1. So this is the dimension of the probabilities, not the batches. Remember, always we have the batch first, and then the y prim index. So these are the class indexes. So this will give us the if this is a petrol car, this will be 0 index. If this is if this diesel car, 0 index, petrol car 1 index, and so on. So this will produce the output something like this. So there is 1, 3, 0, 1, and so on. So this will be the output. So that is that, and then the same will go also here. So it will also produce the output like that. So now we have these two lists of real indexes of cars and predicted these fuel types. So real fuel types and predicted fuel types, and then what we can do is we can use some Python interesting way how to write. So we can just compare these lists. So this will produce the output of true or false. So true where they matches, there will be the true, false, and so on. So this will produce that kind of list. And then, as you know, in C languages as well, C++, C, that booleans, when they are converted to the float, becomes, if that's a true, then it becomes 1. If it's false, it becomes 0. So we can just multiply by 1 and it will produce these values. So that's that. Then we calculate torch mean. So the mean value of all of these combinations, except it's hopefully it will work. So and then item. The item means, so again, let me show you. The item, remember to converting to the numpy, right? So if I have some tensor.data numpy, and I select first element is exactly the same as t item. So this is kind of strange syntax from the torch, but this is exactly the same thing. So if I run it, hopefully we will start seeing the accuracy. So yeah, the accuracy right now is at 54%, and it kind of jumped up and then stays, I guess, hopefully, if everything is right. It just jumped up and stays at 54. It might be also because I'm not using the weights now. Need to double check if there's no bug. So to double check, we can just add some breakpoints, see. So these are, and we can even see the results. So this say 0, 1, 0, so on. This says all of these are 2s. Then we compare these. Then we get probably booleans. Yeah, true, falses. Then if we multiply this by 1, we get 0, 0, zeros. Then at the end we get accuracy. Accuracy is 0 initially. So that, yeah, it works. So they're adding the way how to calculate accuracy based on the highest probability in the distribution. So that we will add. And the last missing piece, is also that we need the weights. So the weights in the loss function, here they are now ignored, but let's add the weights as well. So the weights, again, we could use the same kind of syntax as before. So y index, just to select the correct index of the class, will be then y data numpy argmax axis v1. So this selects the class indexes. Is this a diesel or petrol car? So the 0 means diesel, 1 means petrol, 0 means diesel, 2 means CNG, 3 means LPG, and so on. So we select those samples, and then we need to select them from weights. The weights are pre-computed. So weights are pre-computed in the data set. So the higher weight is to the class, which is rarely found. So when there is a class which is not as often seen as other classes, we want it to be more important. So torch float tensor data set full weights, somewhere was the weight y weights. Then we use y index here. So this is good. This is good. And then the last kind of trick is that this will produce vector without batch size, but it will not work to multiply it. So we need to unsqueeze it. Unsqueeze. So unsqueeze, I will explain. So the squeeze, unsqueeze, and changing the shapes do not change the data. So if I had the list of these guys, so if I had this list, the unsqueeze means I'm just adding another bracket around it. I can also, of course, unsqueeze it in other way. So just a second. So not minus, so okay, so this will not add the bracket like that. Let me see. Okay, so this will actually do this. So -1 means the inner like that. So it's not changing data, it's just adding extra dimension by adding extra those brackets. So and then here multiplied weight, and that's it. So if I run it, hopefully we'll see something interesting. Oh no, something is wrong. The weights are none. Oh no, it's not implemented here. Okay, so I will quickly implement it. You can catch it up a little bit later, but basically the main idea should be understood that the loss function is different for samples which have less sample from that class. So samples which are rarely found are more important than those who are found many times. So now I'm in the slide 19 adding this thing, and then quickly add the way how to calculate weights for you. So the way how to calculate weights, because I don't want to spend too much time on this thing. So let me add here the weights calculation will be this thing. So I'm adding this also to the Jamboard, trying to run it now. Hopefully we'll see a little bit different result. So the accuracy now is down. Something is maybe not okay. Okay, interesting result. Should not be that accuracy is down. So add here the breakpoint, see what we get here. So the weights are 4,000, 3,000, 57, 338. So they are pretty aggressive weights. So, and we are, what about the adding them to the loss? So I'm adding a breakpoint here. Well, this is this. It's a bit strange. Should not be that values. Dataset full weight. Okay, it somehow changed the weights. Should not be that. Okay, it's no. Okay, that was not the weights, those were the counts. The weights are actually these 1.8, 2.2, 100. So what about, let's try to add here a higher value. Okay, it's no, it's much worse. Lower value. No, I'm not sure, so we'll see if this one is okay. Okay, the accuracy, I guess, went up. Well, it's still quite bad. Okay, I need to look, so maybe there is some problem here, but I don't think. What about this thing? Oh, it shouldn't be that, so this is correct. -1, weight. Axis, this is correct. Okay, now it's working. Okay, so something was wrong regarding, not sure about why argmax1 did not work, but argmax -1 worked very well. So I need to look at that, but I will add this as well to the Jamboard. So that works. Okay, that works then. Okay, good. So this is this. Then let's look a few last slides, not regarding anything to code yet, but just to explain. I have like a small homework task for this exact task. If you want to do it, if you don't absolutely want to do it, then it might be a little bit difficult later. But it will not be a huge task. So there is the there is the link to material regarding the confusion matrices. Okay, don't like it, so just a second. new private window. We'll open it here. Just a second. This is
You
annoying.
get the premium membership for $5 a month.
Yeah, like the funniest thing is that if you are a writer for Medium, then
You still have to pay, right?
yeah, like I mean, like everybody pays, you know.
Yeah.
So anyway, here the confusion matrix looks something like this. So the idea is that, or for example here, so the predicted class is here and the true class is here, and you are calculating how many samples are hitting the correct cell. So if I'm predicting that this picture contains apple, and it really contains apple, then I add +1 to the top row. So if I'm predicting that this is an orange, but it actually was an apple, then I add +1 there, and so on. So you kind of fill the matrices, and then when you fill these matrices, this is very useful because you see which classes are confusing with each other, and then you can calculate these precision scores. So that will be as a homework. It will be the example given as well how to do this. So that's that part, and just the final words. Where was it? Okay, so this is the correct window. Okay, here we are. So the confusion matrices should be done, right? So now you see that using the PyTorch, right, you can do basically amazing things without calculating the gradients. So when you train the models, at some point you will start feeling very smart, but actually these deep learning libraries, as you see, do a lot of work for you. Because like before, you looked at how to work with matrices, you look at how to work with the, yeah. Sorry?
The face cam is covering the...
Ah, funny.
Yeah.
Yeah, that was not expected. So yeah, so this image I think explains quite a few things, and finally this one, please. So please do not be like a Friday evening. Let's close everything down, and then on Monday it will be like, what is this, you know? So. When you have an option, then when you have like a few minutes, you know, go over it, try to look at this confusion matrix calculation, try to implement it. We'll help to fix it on Monday, you know, but not just drop it completely, because like we're quite learning with very fast pace, you know. Okay. Yeah. So that's it for today. Yeah. So hope this was interesting, right?